Welcome back, and we are going to wrap up invertible functions by talking about some properties related to them. So first, I want to give you two inverse functions, so the square root of x minus 1 and then x squared plus 1, and then on a particular domain when x is greater than 0. And so I just want you to look at it and tell me what you notice. And so if we look at it, here we are. I put both of them in decimal so you can see the square roots in red and the half parabola is in blue. And just so you know, if you want to restrict the domain, you have to put it in curly brackets and decimals. But here we are, and I'm just kind of curious if you notice anything. So pause the video and talk or discuss anything that you notice. Okay, well, I notice that if we look at kind of where each function begins, so this point here, right, that's 1, 0. If we look at where this other one begins, that is 0, 1. Oh, okay. Similarly, I could look at, like this point, 1, 2, and then this point is 2, 1. Ish, okay, if you get it on there exactly. And then it looks like, again, like they're kind of almost mirrored over some line kind of that goes right in between them, okay? All these are good noticings. Maybe you had the same ones as I did, maybe you had some other ones, and hopefully yours were equally as rich as mine. So, when we look at properties related to invertible functions, there are a few that are very important. First of all, there is symmetry. Okay, this is a formal property. There is symmetry. Okay, of the function and its inverse. Okay, over the line y is equal to x. Now, why is it that line? Well, think about the process that we went through in finding the inverse functions. Didn't we end up switching x and y? So it makes sense that if x and y switch, that there's going to be symmetry over this line, like it reflects. Okay? And then we also notice that, like we had 0 or 1, 0 and 0, 1, 2, 1 and 1, 2. So if AB is a point on f of x, then BA is a point on f inverse. Okay, so again, this means f inverse of B is equal to A. Okay, and that's again because of the domain, or not the domain, the changing of x and y. Okay, so again, the inverse function, when we found it, we had to go through and change those. Okay, and then this actually brings up an interesting thing to look at. If we think about f and f inverse, okay, and we look at the domain and range of each of these. So here's the domain, and here's the range. Okay, let's call the domain of f AB. I don't know what it is, I'm just making up something random. And then range is CD. Okay, because of this changing of x's and changing of y's, really the domain of f is the range of the original function, so those two are connected. And you might then guess that the range is AB, which is also the domain of the original function. So this is correct, and actually one of the most critical parts of inverse functions. So if you know the domain and range of one, you know the domain and range of the other, because they switch. Again, we interchange x and y, so boom, there it is. Okay, a couple examples that hopefully utilize some of these properties. Okay, so we want to know what the inverse, so here's a table of values corresponding to x and f of x. We want to know the inverse function value of 2, and then, so this might be one of those scenarios where, like, okay, you're giving me some information about Earth, and then you ask about information on the moon. Well, I have no idea. Actually, you know more than you think. If we write this out, okay, so this is f inverse of 2, and we're just going to call this a value, I don't know, let's call this k. So then we know on f inverse, right, we have this point that is 2k. Well, when we look at the function, right, don't we end up having the domain and range switch? So we would be looking at k comma 2. So in the original table, is there something where we can see the y-coordinate is 2? So my coordinate is 2, y-coordinate is 2. Oh, there it is. So k is actually equal to 1. And I actually didn't have to do any math. Okay, so this whole thing is equal to 1. It's just using the domain and range properties. So again, switching the x and y coordinates. Okay. Now this one is more of a canonical example, so something that's like repeated over and over and over. So we want to be able to sketch f inverse from this. Okay. So what we know is that, I need to zoom out just a smidge here. We know that for inverse functions, they're symmetric about the line y is equal to x. And I'm going to try and draw that as carefully as I can here. Well, you get the point. Okay, so here's the line y is equal to x. So it should reflect over this, and so you don't really want to just go sketch this willy-nilly. It's nice to find some points. So I would say we know this point at 0, 2. So this is point 0, 2. So then I'm going to have a point at 2, 0, right? So that's going to be this one. Okay, and then I find another point at -1, +1. So -1, +1. Those coordinates interchange, so I'm at 1, -1 for my new point there. And I don't know, let's say I find another point. I'm going to call this point a triangle. And so triangle looks to be at like 1/2, 4. So 1/2, 4. So then I interchange those, so I'm at 4, 4 and then 1/2. So that would be the inverted point here. So then when I now sketch the graph, okay, so 3 points is okay-ish, but what I'd end up getting is something that looks like this. Okay, oops. And I'm going to call this f inverse. Okay, but to sketch f inverse, I'd recommend finding points, find their coordinate representation, and then for the inverse function, switch the coordinates. Okay, and that's the 3 big ideas related to inverse functions: symmetry, the points change, and then the domain and range change as a result.